Hello everyone, this is Mr. C here, and I'm going to help you out with some related rates. Let's get started. The first question says, a small balloon is released at a point of 150 feet away from an observer who is on level ground. If the balloon goes straight up at a rate of 8 feet per second, how fast is the distance from the observer to the balloon increasing when the balloon is 50 feet high? So that's a lot of information. Let's break it down. It's always a good idea to draw a picture when we want to try to conceptualize what they're asking us to do. So here's our observer over here, and maybe here's the balloon, but the balloon's going up. So maybe at some point it's like this high right here. And if you notice, it says it goes straight up. So that means it's moving in a vertical fashion like this. But this horizontal distance here is not changing from the balloon to the observer. No matter how high the balloon goes, this distance here is not changing. But if it's at some point, like right here, then we can draw this line here and we have a right triangle. So what I'm going to do, I'm going to erase a little bit of this stuff. Balloon's going up like that. Maybe we'll put that up here. So the distance from the ground, from the balloon to the ground, we can call that distance some distance A. Okay. And from the given information, we know that the small balloon is 150 feet away from the observer on level ground. So at that starting point. So this distance here is always going to be 150 feet. It's not going to change as the balloon rises. Okay. What are we trying to find though? We're trying to find how fast the distance from the observer to the balloon is increasing. So at any other point other than the initial point when the balloon's on the ground, that is going to be related to this rate here, the rate of change of this side, not this side. Remember, this one's not changing. And this side doesn't have anything to do with the observer. So we know we want this rate of change. Let's call this C, as we usually do for the hypotenuse of a triangle. Okay, so I kind of hinted, right? We have a right triangle. There's an A here. Well, this isn't changing, but we could maybe call that B. And this is C. Yep, we're going to be looking at the Pythagorean theorem. So A squared plus B squared is C squared. And we care about the rate, so we are going to differentiate both sides with respect to time. Okay, and when we do that, we get, well, using the power rule, we have 2a. But remember, a is not our variable we're differentiating with respect to. So we need this term here, this dA dt. It's the rate of change of a. Similarly for b, same power rule, but now we've got b's. And really it's the same thing again for c. Okay, I see some 2's here, so if we divide everything by 2, all those 2's go away. So we mentioned before how we were going to call this B, but that B isn't changing, right? It's always going to be 150 feet. We can interpret that to be dB dt is going to be 0 feet per second. It's never changing. So if I plug in a 0 here, this term goes away. So all I'm left with here is A times dA dt equals C times dC dt. But we have a problem here. We don't know what C is. Well, we can find out what C is by using that Pythagorean theorem before we differentiate it. So here I have A squared plus B squared equals C squared. We care about this when the balloon is 50 feet high. So we're going to let A be 50 feet. B is never going to change. So it's 150. And C is what we're trying to find. And I forgot my squares here. Okay, 50 squared is 2,500. 150 squared is 22,500. If we add those together, we get 25,000. And then we want to take the square root of both sides. We're left with C equals, well, we could put it into the calculator or, use prime factorization, but we can just leave it as this for now. It's all going in the calculator later. All right, so back to the related rates portion of this problem. We know that we care about this when the height from the ground to the balloon is 50 feet. So that's A is 50 feet. dA dt is the rate of change of that balloon. It is increasing at a rate of 8 feet per second. C we just found, it's the square root of 25,000, and that is feet. And dC dt is what we're trying to find. All right, so we have three numbers in our equation and one thing we're trying to find, one unknown. That means we can solve for this unknown. All we have to do is divide both sides by the square root of 25,000 feet. So that'll go away. Notice here that we have feet on top and feet on bottom. Those are going to cancel as well. Okay, and if you were to plug this into your calculator, you would get dC dt is equal to 2.5298 and more stuff. Okay, and we need units for this, right? This number in and of itself is meaningless without units, so we need units. And the units we're left with are feet per second, which within the context of this problem makes sense, right? If the height of the balloon is changing at a rate of something in feet per second, that's just a distance from the ground to the balloon. We would expect the distance, another distance, to have the same units of change, feet per second. But we're not done here, right? So just like we need our units, we also need to interpret this in terms of the problem that we were asked. So the way we could do this is saying when the balloon is 50 feet, above ground, the distance between the observer and the balloon is, okay, increasing or decreasing? Well, this is a positive rate of change, so we're going to be increasing at a rate of about, we can round to 3 decimals, 2.5, what's it, 230 feet per second. All right, moving on to the next one. So a man throws a stone into a still pond, causing circular ripples to spread. If the radius of the circle increases at a constant rate of 1.5 feet per second, how fast is the enclosed area of the ripples increasing when the radius of the ripple is 3 feet? So last problem, we kind of just jumped right into like a math diagram of this problem, but we don't have to do that. We can first start with like a picture of the situation. So picture a bird's eye view. So a view from above a lake or pond or whatever. And I just drop a rock into the lake. And then like a little bit later, we see a ripple. So here was where the rock was, but this is the first ripple. And then a little later, that ripple is no longer there. It's a little bit bigger. And you can keep doing this. So at some point, we're going to have, well, there's a circle there representing the ripple. There's a circle here representing the ripple. We have a circle. Okay. We care about the area. And we care about the radius too. So the radius would be from the center of the circle, of course, to the edge of the circle. There's our R. And we can represent the area of a circle with the equation area equals pi r squared. We know the rate of change is dr dt equals the rate of change of the radius, dr dt equals 1.5 feet per second. And we want to find the how fast the enclosed area of the ripples is increasing. So the rate of change of the area when the radius is 3 feet. Okay, so we need to differentiate this area equation with respect to t. So if we do that, then we get dA dt on this side. And again, similar to before, we have this power rule. So this is just a constant multiple of pi, right? So that's going to stay. But we bring down the 2 and we reduce the power by 1. And again, we're differentiating with respect to time, not our variable for radius. So we need that dr dt term. All right, and now we just input the stuff we know. So we are trying to find dA dt. We know that's equal to 2 pi times, well, we care about this when r is 3 feet. And we know that the rate of change of the radius, dr dt, is always 1.5 feet per second. Okay, and then we just multiply this out. 2 times 1.5 gives us 3, times 3 is 9, times pi is 9 pi. And we need to take care of our units too. We have feet times feet per second. That gives us feet squared per second. We do need that feet squared part, right? Because we're dealing with the rate of change of an area, and areas have square units. But again, this is not the end of our problem. We need to reinterpret this problem or this solution within the context of the problem. So we can do that by saying the enclosed area of the ripples is increasing, again, increasing because this is a positive rate of change at a rate of 9 pi feet squared per second, excuse me. And this is the key part, when the radius is 3 feet. Moving right along. All right, this is what I call a shadow problem. I always had trouble with these, so I'm going to take it slow. A 6-foot tall man is 10 feet away from an 18-foot light pole. Okay, lots of numbers. The man walks towards the light pole at a rate of 1 feet per second. We want to find the rate of change, find the rate at which the length of the shadow is changing. All right, before we care about any of those numbers, let's draw it. So here I have, a light post. And I'm not an artist, okay? And we have a man. And if the light's shining down on this man, right, we can kind of imagine that the tip of the shadow would be dictated by how high the man is and the distance he is from the light post. So the man is 6 feet tall, and the light post is 18 feet tall. And as he moves, right, he's moving towards the light post at a rate of 1 feet per second. So as he moves, this distance is changing, right? The distance between the light post and the man is changing, but also the distance from the man to the tip of the shadow, which is the length of the shadow, is also changing. So we need two different variables to represent this situation. Let's call them X and Y. So this one's going to be X. This one's going to be Y. Which means that whole thing here is X plus Y. Okay. A key observation here is that because the man is standing straight up and because the light post is presumably straight up, these are parallel things, parallel lines. And since they're parallel and their other two sides, like see how this little triangle here is like this side of the little triangle is just part of this longer side, just like this side of the little triangle is just part of the longer side right here. Because that's the case and because these lines are parallel, that means these two triangles, the big right triangle here and the little right triangle here, are similar triangles. Because we have similar triangles, there is a property of similar triangles that states similar triangles have proportional sides. All right, so we can set up a proportion of the side lengths of the little triangle and the bigger triangle, all right? So the ratio, let's look at the bigger triangle, from this side to this side would be X plus Y over 18. And we know that if they're proportional, the bigger triangle and the little triangle, we can set it equal to the corresponding ratio. So we looked at this one for the numerator, X plus Y. That means we're going to look at this one for the numerator of the next part. We looked at 18 feet for the denominator of the bigger triangle's proportion. That means we're going to look at this part, its corresponding part, the denominator of the little triangle, 6 feet. All right, and then we cross multiply. That gives us 6 times x plus y. Well, that's 6x plus 6y equals 18 times y. All right, if we subtract 6y from both sides, we get 6x equals 18 minus 6 is 12y. And if I divide both sides by 12, you get y equals, well, 6 over 12 is a half times x. Now, if we differentiate this equation here, right? This equation relates our two variables, and we care about the lengths of these two things, so we want to do that. If we differentiate that equation here, we get again, constant multiple rule, we keep that, but now we have the rate of change of x with respect to t, and the rate of change of y with respect to t on the other side. All right, let's talk about what we know, right? So we're trying to find the length of the shadow. That would be this y value here, right? We're trying to find the rate of the change, excuse me, of this length. So we're trying to find dy dt. And we know that this x is getting smaller at a rate of 1 feet per second. So if it's getting smaller, we want to make that a negative rate of change. So dx dt, we're going to say is negative 1 foot per second. So if we plug that in here, we get negative 1 times a half. We get the rate of change of y with respect to t is negative a half foot per second. Now, what's really interesting about this is, right, we started when the man was 10 feet away. Do you remember using 10 anywhere here? We did not. And the reason we never ended up using it and we still got a value for the rate of change is because this is a linear function. And when we take the rate of change of a linear function, right, think of a line. When you take the derivative of a line, you just get a constant. So it doesn't matter how far he is from the light post, this rate of change is going to stay the same. So we could say that the length of the man's shadow is decreasing at a rate of 1/2 feet per second when he is 10 feet from the light pole. Or we can generalize this and say, who cares about how far away he is? It's always going to be decreasing at this rate. So we can say the length of the man's shadow is decreasing at a rate of 1/2 foot per second. Again, as the man approaches the light post. You can say, just to reiterate, you can say when the man is 10 feet away from the light post, but this does generalize to however far away he is from the light post. All right, part 2 of that problem asks us about the rate of change. The tip of the shadow is moving. And in order to solve this, right, the tip of the shadow would be around here. We need some reference point that isn't moving. So the man is moving. We don't want to use that as the reference point. Let's use the light post. The light post is fixed. It's not moving. We can represent the tip of the shadow by talking about this distance here. Okay, so the distance from, let me just quickly redraw this here. We had a man there. This was X, this was Y. Let's call this Z. For the equation, that represents the distance from the tip of the shadow to the light post. So we now want to find dz dt. Okay, and we know z is equal to x plus y. If we differentiate both sides with respect to t, we get dz dt equals, well, dx dt plus dy dt. We already found those from our previous problem. We were given dy dt, which again was the rate of change of the shadow. And we were sorry, we found dy dt and we were given dx dt, which is the rate of change of the man. So this one was -1 feet per second plus -0.5 feet per second. And that gives us -1.5 feet per second. And again, we can write our answer in the context of the problem, and you could do that by saying the tip of the shadow is getting closer to the light post at a rate of 1.5 feet per second as the man approaches the light post. All right, a couple things to say about this. Again, we have this as the man approaches the light post because we never used that 10 feet away part in our problem. So you could say, you know, instead of as the man approaches the light post, you could say when the man is 10 feet away from the light post. That's fine, but it does generalize a bit better. The other thing I want to mention here is I wrote the shadow is getting closer to the light post, right? So we were never told that, you know, moving left or right was positive or negative, right? So we can't just say, hey, I drew my picture like this. So if he's going to the left, it's negative, and going to the right, it's positive, right? I could have drawn it flipped, and then that would flip it. So let's, instead of using positive and negative, let's use our reference point. We chose the light post as the reference point. We know the shadow is getting closer to the light post as it decreases in size. All right, last one. A cylindrical tank of radius 10 feet is being filled with wheat at a rate of 314 cubic feet per minute. How fast is the depth of the wheat increasing? And it gives us this nice tip that the volume of a cylinder is given by this expression or equation here. All right, let's draw it. So let's hope this goes well. These are not the easiest to draw. All right, we know the radius is 10 feet. And it's being filled with wheat. The height of this, well, actually, let's imagine we've already put some wheat in here. So maybe it's full up to like this point here. All right, so the height of the wheat is actually going to be given by this part right here. And we know that the rate the wheat is being put into the cylindrical tank is 314 cubic feet per minute. Whenever we see cubic, we want to think volume. So, and this is a rate, right? Per minute indicates it's a rate. So this would be the rate of change of our volume, or dV dt. Right, and we want to know how fast the depth of the wheat is increasing. In other words, find the rate of change of the depth or height, which is dH dt. Okay. Something to point out here, this radius is not changing, right? The height's changing, but it's not like the cylinder is expanding or anything. So if we use this formula here for the volume of a cylinder, we can input R immediately because we know there is going to be no rate of change. So when we do that, we have pi times r, which was 10 feet squared, times h. And if we differentiate both sides, right, this is equal to v. So we have dv dt equals, this is just a constant multiple. We can pull that out. And the rate of change of h with respect to t. Okay, we know what dv dt is. It's 314 feet cubed per minute. And this simplifies to 100 pi. And this is what we're trying to find, dh dt. So we divide both sides by 100 pi and we get, well, I'm not going to put it in a calculator. Okay. And lastly, we do need our units, right? This is a rate of change of height. Height is like a measure of length or distance. So we would expect that to have linear units. And it's not seconds, it's minutes. Oops. Another way you can think about this, right? If I had inputted my radius and I actually wrote the units, this would be feet. I'm squaring that, so I have feet squared, right? This was feet cubed per minute. And then I divide both sides by feet squared, and I'm left with feet over minutes. Last thing we want to do is write this within the context of the problem in words. So as wheat is being put into the cylindrical tank, the rate of change, or rather we could say the height of the wheat is increasing at a rate of that feet per minute. Another thing to notice here is similar to the shadow problem, right? This formula here is not a linear function, right? We have r squared and we have h, but remember we plugged in something for r and we got this little intermediate step here, right? This is just a constant times a variable. So I have a variable equals a constant times a variable. I have no powers here. This is a linear function if we take it as a function of h, right? So there's no r in this part. So again, all this is to say, this rate of change happens no matter how high the wheat is. All right, I think that's all. Thanks for watching, and I will see you in class.